In section 11.4, we'll look at energy considerations in planetary and satellite motion. Our goals here are to use energy considerations to solve problems involving orbital motion and use energy to determine escape speeds and explain phenomena observed around black holes as well. Now, so far, we've analyzed orbits in terms of forces and angular momentum. What we're going to look at now is an energy perspective. Consider some mass m, maybe a little mass, that is moving with some velocity around a much more massive object. We'll call that capital M, where capital M is much, much bigger than lowercase m. So this might be like a planet around the sun or a satellite around the Earth. Now, we will treat both of these masses then as an isolated system, where the larger mass is basically at rest in the center, and the smaller one is going to be orbiting around that. Now, here we're going to look at mechanical energy being conserved, because the total mechanical energy, again, in an isolated system would be conserved. So here we could look at mechanical energy being the sum of the kinetic energy, K, of this object actually moving around M, and its potential energy, U, because it has some distance away from that center of mass, and is going to have some potential energy due to gravity. So the total energy could be thought of as its kinetic plus its potential when we add up that mechanical energy. Now remember, when we look at a pair of masses separated by a large distance, we don't write U as like an mgh. U instead is given by that equation of that negative gmm over r. We studied that earlier on. Now remember, for this equation, we said that U would actually go to 0 when r goes to infinity. So when you get infinitely far away from this large mass here, whether it be the sun or a planet, whatever that might be, when you get infinitely far away, that's when you no longer have any potential energy. Now, because we would use this as our equation for potential, then when we sum up our total mechanical energy, it's a 1/2 mv squared, which is K, plus the U value of negative gmm over r. Now, from this equation, it's easy to see that your total energy could be positive, it could be overall negative, or it could be 0. That would totally depend on your values of V and R that you're plugging into this equation. Now, for a bound system, this might be something like a planet moving around the sun or a satellite in orbit around Earth. Bound systems are things where it can't ever leave. It is bound or stuck to be in that orbit. In these bound systems, your total energy is actually going to be a negative value. Here you would have your energy line actually intersect the potential energy curve, and where it intersects that potential energy curve is what you would call like your turning point there. Your separation distance R can never be any greater than this R max, essentially, that you would be able to come out to. So if your total energy was down here in the negative region, then you would have, again, a point where you intersect that curve, and this would be a bound object. You can't get any further away because your total energy is intersecting that curve of that potential energy there, and you don't have anything else to put in. Now, an unbound system, on the other hand, would have a total energy which is positive, meaning that it can move to any distance r away. This would be like a flyby comet that can move infinitely far away. If we were to look at where this might end up on the graph, it would be somewhere up here, where it doesn't intersect this portion of your potential energy curve and can get as far away from that object as it could ever need to or want to. It's actually pretty easy to prove that your total energy would have to be less than 0 for those bound systems. So let's again look at a circular orbit, because those are really easy to analyze. Again, you have something creating that gravitational field in the center, and then an object moving around that, and we'll say that this is a circle. If it's a circle, again, the force that we're looking at here is going to be the force of gravity, or gmm over r squared, and we can set that equal to ma, where again, this a, because it's moving in a circle, is going to be a centripetal acceleration, meaning that we'd set our force equal to mv squared over r. Now, all I'm doing here is multiplying both sides by a half, so I can put a 2 on the bottom of each of these fractions. Now, since we know that total energy from the last slide is going to be a 1/2 mv squared, or K, minus the GMM over R, or U, just combining those two pieces. And since we also know from here that 1/2 mv squared is GMM over 2R, we're simply going to plug this piece in for this piece. And what we end up with is this GMM over 2R minus GMM over R, where again, if we gave it a common denominator, we would really end up with a -1 GMM over 2R. What we see now, again, is that first of all, we do have a negative in this case. So total mechanical energy is a negative in the case of circular orbits. And you can see that your kinetic energy of that object in the circular orbit was actually equal to half of your potential energy in that system. Now, the total mechanical energy for an elliptical orbit is also going to be negative. The only thing you'd have to do is replace the R that we have here with an A instead. Again, that was the distance along that semi-major axis, so that we come up with this total energy equation equal to -GMM over 2A. So what we're finding is that the total energy, the total angular momentum, and linear momentum of a planet-star system, these are all going to be constants. So let's try an example. Let's say that you have a satellite that's moving in an elliptical orbit about the Earth. So we'll have the Earth here, and it will be moving in elliptical pattern. We'll kind of make it a really obvious ellipse here. And you know some things about this orbit. You know minimum and maximum distances from the surface of Earth. So minimum distance from surface of Earth is 400 kilometers. And max distance from surface of Earth is 3,000 kilometers. And you're being asked to find the speeds of the satellite at apogee and perigee. You need to remember which one is which. It might be helpful to think of the A here. A stands for away. So at apogee, that was when it is furthest away from the object that it's orbiting, or aphelion if this was around the sun. And perigee is where it is close. So we'll put a little A here and a little P here to help remind ourselves of that. Now, to begin this problem, remember, we said that there's a few things that are conserved. We know that angular momentum is conserved, and we also know that energy is conserved. So we could actually start this with a conservation of angular momentum. That the angular momentum, when you are close at the perigee location, should be equal to the angular momentum when you're away at the apogee location. So we could write this angular momentum as an MVR, since we do in fact have some of those values, and we could write those down. Now the mass is the same on either side, so that really doesn't matter. And really what we need to think about here now are, what are these R values? Remember, R values here always should be measured from the center of mass, which is not actually what we were given. We were given distances from the surface of Earth, which means that we need to come back here and think about, well, from center of mass of Earth out to this orbit, where am I? So when I come over to this side of the equation, over here, I'm going to have an R value where I was close by of the 400 kilometers, so that would be in meters now, plus the radius of the Earth, where the radius of the Earth, if you were to look that up in your books, is about 6.37 times 10 to the 6th meters. Now over here on the other side, I'd have my VA, and I would have my 3,000 kilometers plus the radius of the Earth. Which means if we go through and simplify this just a bit, you'd find that VP is equal to about 1.38 VA. So I've kind of got one equation here, and I've solved for one of those variables to kind of rewrite it in terms of the other variable. Because again, my goal is to really find the velocity in both of these places, meaning that VA and VP are both the variables that I'm looking for in this problem. Having two variables, I have to have two equations. And so far, I've only set up one. I've only set up conservation of angular momentum. So I could set up another equation, which would be conserving energy, where my potential and kinetic at each of these locations, the close side and the far side, that also has to be equal because energy, mechanical energy, is going to be conserved as well. So I'd have a negative GMM over my total distance of RP over here. Again, I'd put in my 400 kilometers plus my radius of Earth. And I would also add on my kinetic energy, or my 1/2 mv squared. And on the other side, I'd have the same thing. I'd have my GMM over, again, the bigger distance. Again, adding in the radius of Earth to account from center of mass, plus my kinetic energy, my 1/2 mv squared. Now, all of these m's are simply going to cancel out. And what I can do now is take this VP in terms of VA. I could plug that in here and then begin to simplify. If you'd like to take a minute, pause the video, and go ahead and do that, you should be able to solve for each of these velocities. Your final answer would come out to be a VP, so at the close position, you would get a value of about 8.27, and that would be kilometers per second, or 8.27 times 10 to the third meters per second. And when you solve for VA, you would get about 5.98 kilometers per second, or 5.98 times 10 to the third meters per second. Now, it makes sense that your VA would actually be the slower speed, because here you obviously have more energy in your potential than you do here. So the object should be moving faster here than here.